Hello, this is Greg Risteman from Olympus. Welcome everyone today to this second webinar in the WeldSight Software Introduction Series. This is part 2, Analysis. This webinar puts an emphasis on phased array and time-of-flight diffraction of flaw analysis of Focus PX and OmniScan X3 inspection data. A demonstration of the analysis workflow in WeldSight software will be given, and unique considerations for the analysis of X3 flaw detectors phased array and TOF data will be explained. Our presenter today is Chris Magruder. Chris has worked for Olympus for 19 years, providing phased array and TOF training to customers of all levels. Chris is actively involved in phased array product and software development at Olympus, with a background specialty in new weld fabrication and in-service inspections. This informational webinar has been scheduled for approximately 1 hour. If you have questions, please type them into the Q&A panel in the lower right portion of your screen during the presentation. If we're not able to get to your questions during the live webinar, they will be addressed personally, either by email or phone after the event. Everyone who registered for this event will receive a follow-up email with links to the archived presentation, whether you have attended it or not. Now, without further ado, I'd like to turn the presentation over to Chris. Chris, take it away.
Hello, everybody. Thanks for joining us. We have a big group today. And again, this is a follow-up from our previous webinar that covered setup and acquisition. And today we'll be doing a demonstration and a UI overview of WeldSight for analysis. The analysis section now includes the OmniScan X3 ODAT file support. What we'll be going through today over the next hour is an overview of the software itself, including the dashboards, some weld bevel and calibration block features, mechanical offsets update, shortcuts throughout the software, creating and saving custom data display layouts and some new data displays that have come online since our last webinar. The display overview for gate and volumetric merge C-scans has been improved. We have new functionality online as well to display today. And to talk a little bit about the display and attributes layer we use in analysis. The weld analysis will also be demonstrated with an emphasis on the active beam set data cursor and trigonometry readings, cursor behavior and shortcuts for flaw sizing and characterization, use of dynamic B-scan and C-scan analysis, how we manipulate color and soft gain for flaw characterization, merge functionality including piping polar views and cursors for geometry correction, and the 3D imaging. The UI overview will also include TOF. So we'll go phased array and the TOF. The TOF in WeldSight very simple, only requires a couple clicks and a short explanation, but we'll be referencing this back and forth from the phased array data, and that includes the calibration functions for analysis, linearization of the B-scan, and synchronization and removal tools. So without any further delay, we'll go ahead and jump into WeldSight software. I'm going to share my screen to start looking at some data files. So our first data file today is going to be a 2 phased array and 1 TOF beam set, typical of vessels, pipes, wind towers, and mini inspections that we do. When we open the file, the WeldSight now supports the X3 ODAT and the Focus PX ODF file formats. When an X3 data file is present, that we'll see it later in the webinar, we'll have an X3 icon here where the form will open and we can see the beam set information. In this data file first, it was an acquisition with the Focus PX, and in the setup and data file, we see the full layer for the beam tool where we have access to all of the beam sets, probe, and wedge information. This will change somewhat when we look at the OmniScan X3 data. An overview of the UI we'll start with, and it's divided into setup, calibration, inspection, and analysis for the workflow. And in the analysis, we won't be connected to an instrument, so there's no indicator that we're connected here. And all of the live functions, such as parts of the UT settings and the calibration functions, are not accessible for offline analysis. The piece is either created from the beam tool in a Focus PX acquisition, or it comes from the OmniScan X3. Supported pieces are plates, axial long seams, and pipes. We import a piece name, the scan surface. We can make changes to the thickness and the length here without updating the original file on the X3 or reconfiguring the beam tool. Complex geometry or a change in weld bevel can be updated directly from the beam tool EBP file, whether this is data from a Focus PX or an OmniScan X3. We also include a default calibration block that can be updated from the OmniScan X3 for the beam tool BTCB file that allows us in the footer to switch between the calibration block directly and the component piece. This is mostly used for setup, acquisition, and calibration, but it's also useful to validate a TCG points in the data file. The UT settings of this file is divided between the general, position, and the element delay information. And in the general tab, we can see that this data file was acquired on high voltage with 100 nanosecond pulse width that was set automatically by either the X3 or the Focus PX during acquisition. The smoothing filter was on, and this is not editable offline. This is a function of acquisition, and a filter, bandpass filter for the frequency of the probe is available here. The mechanical offsets for both the scan offset of the individual beam sets for the phased array and the Toft are available under the UT settings position and are editable, including the index offset. These mechanical offsets are just layers we place on the data for the rulers and the overlay, and they can be changed or amended at any time. The beam information here is all directly inside the wedge and updates for every beam set and beam. The digitizer we review in analysis for verification of the UT setup on the horizontal axis. A 5 megahertz probe digitized at 100 megahertz with a compression factor of 10 generates a sound path resolution of 0.16. So the compression setup that we do our analysis from the original acquisition is very important. And at a 0.16 millimeter resolution, which is typical of a 5 megahertz probe setup, we have a very good resolution on the S scans and A scans for any amplitude-based or fracture mechanic type of acceptance flaw sizing and characterization, including cracks, hick, HTHA, leaching, and these types of characterization that require a very high resolution A scan and S scan image. The gates are digital, soft gates. They can be updated at any time, and with process while moving selected here, the gates will dynamically update the C-scan data without me having to let go of them. We're going to see lots of examples through the demos of how dynamic analysis, watching something move either from rolling a B-scan or the gate data, is the easiest, fastest ways to find flaws, especially in a V-weld with lots of geometry. So as I move through the depth of the gate on the skew 90 here, I can see 1, 2, 3, 4, 5, 6, 7, 8, and we're going to know that these are porosity and slag right in the middle of the weld where they're supposed to be. 9, 10, okay, that one we've saw before. So this is about 10 out of the 11 flaws in this sample we can detect just by rotating moving the gate through the volume of the weld using a depth window like I just demonstrated. The modes of depth, path, or time, and their position can be changed at any time without truncation of the data. These are pure soft gates, which means that the precision is also dependent on the UT resolution. It doesn't have an independent 10 nanosecond resolution inside the gate area. The TCG here, we can see, I'm going to switch to a single beam set display. The TCG is available here for viewing. It could also be extrapolated, exported from either the X3 or the Focus PX directly in an Excel table. And we can see here for each beam set, as I updated here, we see the TCG. We can see that my deepest TCG point of 50 millimeters is sufficient to provide the full skip through the full volume of the 22 millimeter weld for a full V skip. So it's sufficient to cover our area of interest. The calibration functions in the header, again, have no value of displaying or any function in analysis mode, so they're disabled. Under the inspection tab, we can see the motion that was the motion settings that were either from the Focus PX or the OmniScan X3. This is a 1,050 millimeter long weld acquired at a 1 millimeter resolution. The zoom window that we see here has a different function in analysis than it would have for acquisition. And what this allows us to do, we set the zoom window, and this is a 1,000 millimeter long sample, but in general, for wind towers, LNG tanks, big vessels of maybe 10 meters, 12 meters or more, we only like to use about 1,000 millimeters maximum on the screen at any time during acquisition. So in analysis, this has a little bit different function in that I can set the zoom window and use a series of shortcut keys to increment through the scan axis. So just for demonstration, and again, if you have a big monitor, we would normally limit this to about 1,000 millimeters on the screen. So an Alt arrow shortcut increments the first 200 millimeters, and successive Alt arrows increment through the weld at the zoom window resolution. To return, we just zoom back in here, and we see the full scan axis. The encoder calculator also has a little bit different function in analysis mode than validating the resolution prior to inspection, in that the reference and measure cursor can be placed on the data, and the scan axes could be recalculated so as to bring a pipe or a wind tower or vessel exactly where it's supposed to end, from 12 o'clock start to 12 o'clock end. So this would remove any scanner drift or any encoder resolution drift throughout the course of the inspection, so that all of the acquisitions would end exactly where the operator determines them to be with the scanner at 12 o'clock. The data statistics here from acquisition are available. So in the file, we see the acquisition version of either the X3 or Focus PX acquisition software. We see the device serial number that was used during the acquisition. And the statistics here give us the total data points on the scan axis. I'm going to turn the cursors on. And if I set cursor at the beginning of the scan and at the end of the scan, I can see the total number of points and the number of missing data points, if any, including the number of adjacent points. So there were no missing data points as an encoder blip or excessive speed here. But as soon as I take them past the scan excess here, I can see those in my statistics. The header at the top of the software includes the navigation for the workflow, includes our display layouts here that we'll see shortly. The gain, both in the UT acquisition gain and software or scan gain that was acquired over reference. This is where we select the active beam sets and active beams as well. You'll see several pieces of information in the header and footer, such as the acquisition rates, the real-time measured. These have no value during acquisition, and they're no value for analysis, and they're only used for acquisition. The dashboard that we see here is turned on and off from the header here, and it includes the start-stop acquisition information for acquiring data, but also the readouts based on gate trigonometry readings and cursor values. An auto 80 set range, which is not used in analysis, turn cursors on and off, and enable the flaw table here. These are the only icons in the software that don't have a label directly on them like these. So we don't have tooltips on these because they interfere a little bit on the UI. So if I double click on the readings area here, it opens the readings form available from preferences. The software manages 3 lists of readings for phased array, conventional UT, and TOFT. When you select the active beam set, like in this case, the skew 90 phased array, I get the phased array layout list for gate readings and cursors. The lists include cursors, gates, sizing, and are independently configurable for the 3 technologies. Adding or removing a value from your list is realized when the list is updated. And again, selecting a TOFT beam set or display enables the TOFT readings and a phased array here. So these are customizable for the different applications, and these live in the preferences, not in the setup file itself. The C that you see in the upper right-hand corner here when we're selecting the display is an indication if the system is in compression or a one-to-one mode. If you were to zoom in, that would eventually go away. When the number of data points or UT points in the data exceeds the number of pixels in the display, the software is in a compression mode. And this is a carryover from procedures that required us to be out of compression mode in analysis. All modern software manages this very well. You'll never miss a pixel, even on a small display. The maximum amplitude is always represented by the pixel that's on the screen. The preferences are available here from the upper right-hand corner, and they're divided into several subgroups, most of which are relative to acquisition, some of which are relative to analysis. So that includes the default for millimeters or inches that we see here. Millimeters and inches can be switched back and forth right here in the footer at any time. We're storing the data always in millimeters, and we only convert it for inches for the UI. In inches, we'll have a 3 decimal precision, and in millimeters, by default, we will have a 2 decimal precision. The data cursors, color, shape, and size can be changed and customized here. The applications will either put us in the X3 environment for defaults that will save us a couple clicks on file open and file save, or the beam tool for Focus PX acquisitions. The UFF enable is the universal file format of OpenView, which is Olympus's SDK. When this is enabled, it allows the data to be saved to the OVD and OVS file formats, making it accessible to the free OpenView SDK that's available on the Olympus website. This allows customization and access to the data file for custom reports, custom algorithms. This is the method that companies like Veriphase would run their assisted analysis software directly on the WeldSight or X3 data files as well. It allows the customization and access to the A-scan data directly. And again, that can be downloaded from Olympus's website for programming and custom reports in C++, and it interfaces directly with the flaw table of WeldSight. So again, these preferences here, when set correctly, will save us a few clicks and put us in the right environment for our typical applications. Any form can be opened and closed from selecting the icon or just double-clicking anywhere in the header information. The forms are also available through several shortcuts in the software, most of which are related to acquisition. For instance, a UT axis ruler here, if I double-click on the UT axis, I get the UT settings. If I double-click on the scan area here, we get the motion settings that we just looked at. The acquisition area will enable the digitizer and so forth. It's just a quick shortcut to open and close forms quickly. The display layouts are selectable from the header, and there's a default list that's included with both the Focus PX acquisition support and the X3 analysis support. Those two lists of default display layouts are available in the installer under the Setup directory. The software installs directly with the X3 defaults, and these lists are mostly designed to support a one-phased array, two-phased array, or Toft beam set. For any configurations other than those, they generally have to be customized directly. So selecting the list here gives us my list of available layouts, and to recreate any list that we select, for instance, the SABC layout typical of an OmniScan, we'll delete all of the windows, we'll name the layout something useful, and we will right-click, split horizontally, split vertically, scale appropriately, select the beam set desired, and we are dealing with analysis only. We're not connected to an instrument, so the setup displays have no value. Under the inspection displays, we'll grab an S scan, an A scan, the sweep B scan, and any display can be flipped and rotated appropriately depending on if we're stacking them vertically or horizontally. We'll grab the amplitude A C-scan here, and we'll save it and move it up and down in priority of our list. Any display that is tagged with a follows active beam set on all of the associated displays will follow the active beam set as it's changed by the operator. Selecting a different active beam set in the header will follow that display. Typical of a single beam set analysis display, we would link to the active beam set so we can change and move around quickly. The three main types of displays for the C-scan acquisition would be the gate A amplitude, such as we see here. And in this gate A amplitude display, we're collecting the data all between gate A here and here. Any data or any detection within the gate A range, regardless of if it's in our area of interest or not, is displayed in this C-scan. And it's typical of TomoView and the OmniScan MX2 and X3 and typical on the market. It's probably the most useful display for gate detections for the easiest analysis. Another type of display is the weld. This is a very similar display, but it only shows the information in the C-scans inside the heat affected zone and weld area of the S-scans. So when using the weld gates, which is here, the weld amplitude, it's very important that we set this has area appropriately. The has area, if coming from an X3 inspection, doesn't exist in the data, so it must be set here. We have a default 5 millimeters that we set on an X3 import, and this can be adjusted here. So when we adjust this has zone and make it wider, we can see that the C-scans update directly. The third type of C-scan that we'll use is the volumetric C-scan. The volumetric C-scan, which is gate A merged amplitude. Previously in TomoView and in the MX2, this required post-acquisition processing and wasn't available live during inspection. So this does not require any manual merge function and can be directly dragged from our display layout list onto the display here. And again, only merging both of these beam sets into a C-scan would require post-processing acquisition. The layouts at the bottom of the inspection here, there's another subset called processing. These are the merged, remapped polar end views that we'll get to in analysis. And again, these can be dragged and dropped on any display, but they're not realized until the merge function is manually performed. The displays themselves are just display layouts. They don't affect the data, and they weren't dependent on acquisition. So I can switch between them, and it doesn't cost any RAM, any additional file size from the acquisition. They're all available all the time, where we don't pay a price for them in RAM, file size, or CPU. The zoom functions are generally designed to be used with a mouse, especially in analysis. It'd be unusual we would be doing offline analysis without a mouse, except if we're in the field immediately after acquisition. So by default, all of the zoom functions are linked. If I use my mouse wheel to zoom in on any area, it's going to zoom the same volumetric position by default on any other beam sets. If I only wanted to zoom a single window, I hold down the Shift key. And we'll do this quite often whenever we're looking on different displays, whether I want the zooms linked or unlinked, that's a Shift key. If I zoom on a single axis, like on the scan axis ruler here, it will only zoom that axis, and use of the mouse wheel quickly can just return to zoom. For the people doing analysis in the field with no mouse directly after acquisition using a laptop, there's also a right-click zoom in. These exist to be able to perform the functions with the touchpad of a laptop and not have to use a mouse as well. There's some other functions like the scroll bars here that are TomoView carryovers for the TomoView users that, again, this would allow the touchscreen people to zoom and manipulate the axes similar to some of our legacy software. Selecting zoom out and turning that off here gets us back to our regular zoom mode. So that was a very quick, brief overview of the UI and the various places we go to turn things on or off, and the navigation through the forms and subforms. Any shortcut anywhere in the software would always be accessible from one of these four menus here or from the preferences we see here. So we're going to continue the demonstration and now get into some analysis itself and talk about some of the flaw sizing under a couple different conditions. So we noticed right away that when I opened up this file, it was saved with the track mode on here, and this is beam set specific. So I would need to turn it on or off on all of the individual beam sets. What this does in analysis mode after acquisition, it automatically tracks the amplitude of the signal in gate A to snap the data cursor to the highest amplitude signal at that point on the scan axis. So it's doing this independently for each of the beam sets. And it allows us to see flaws immediately without having to manually drag the data cursor to the location. And again, on some of our analysis tools, that's going to interfere with some other functions, like when we link the data cursors and snap to peak functions. So just always be mindful if that's on or off, and some of these functions we'll turn on and off through our normal workflow. So a little bit about amplitude first on this file, whether from a OmniScan X3 or a Focus PX application, I can see that there was a 13 dB set at the end of calibration when the operator hit set reference gain. And he did that for each beam set. There's an additional 3 dB of software gain saved in this file. So had there been hardware scan gain acquired either with the X3 or with the Focus PX, I would have seen it here. And then once we're in analysis mode, like we are now, this field is software gain. So it's real important. A reading that we use often, and it's the primary amplitude decision reading for the ISO acceptance criteria, like as used in wind towers and other products similar to that, is the amplitude in dB of the signal in gate A relative to the reference amplitude. So what this means is when I set the reference amplitude at 80% from the time of my calibration, this ADBR goes to 0. Then I can look at the amplitude of any signal in my data, and I can see its relative amplitude to my original 13 dB here. It ignores any software or hardware gain above that or below it. So this reading will always be the same no matter how much software gain I've applied. This is 0.51 dB over my reference sensitivity. And at 0 scan gain, okay, it's an 84% amplitude. And again, this reading doesn't change. It always gives me the amplitude of the flaw relative to my original reference gain that we see here. We'll take a look at a couple flaws. I'll go back to the original 3 dB over, and let's take a look at a couple flaws. Now, sorting through 2, 4. So here we have a detection right on the edge of our has zone, a 2-probe detection. Anything in this area would typically be a small little crack, or in this case, a qualification notch that we would need to detect, locate, and size. So we're going to look at a couple flaws, and we're going to perform sizing based on an amplitude or a time of flight type of sizing technique. And in this case, a time of flight. The amplitude plays a very little role in this. One of the first indicators are I've got a very good tip right on this signal. So this is the tip of the indication. That's the corner trap of it. And we can see it from both probes detected at a high at a very high SNR. So I'm going to move to a single beam set layout on the SKU 270, and I'll characterize that in the B-scan here, and we'll size this flaw. So again, the amplitude does not play a big role in this sizing, and had we not been able to get a tip, like example we'll see later, this would just be a close estimation of that flaw's size. So I'm going to bring on my cursors on. I'm going to put a cursor at the scan at the UT position right in the center of the tip, and right at the bottom, I'm going to switch this to the 270 side, the near side, and I'll resume, bring this in here. So I've got a very clear tip. I'm always going to place the red cursor first because the blue cursor trails the red cursor. So get in the habit of using the red cursor at the top and on the left, and the blue cursor on the bottom and at the right. So if I'm going amplitude tip to corner trap, this would be the same sizing technique as in conventional UT for the relative arrival time technique. I'm taking the signal's time of flight from the tip to the corner trap of the crack or the notch here. So I have a through wall dimension of about 2.23 millimeters. Okay, if I were to put this cursor here on the bottom, assuming that we know the thickness of this tip measurement now becomes the absolute arrival time, meaning that we're only taking this through wall dimension and we're assuming it's connected and measuring it from the bottom directly here. Okay, we could also get the gate data from that tip by manipulating the gate directly over it. So if I created a small window here and brought my gate down right on that tip and zoomed in on it, this DA reading would be the trigonometry reading to the time of flight of this. So the gate readings are dependent on the angle accuracy and the velocity of the component. And if they're in the second leg, they're dependent on the operator knowing the exact thickness of the component. The relative arrival time and the absolute arrival time sizing that we just did are not dependent as much. So I'm going to do my depth and height sizing here. I'm going to record the flaw at the highest amplitude peak here. I'll zoom back out, and now I'll do my length sizing. You can never know the real length, height of a flaw that's saturated. So we will bring this flaw to 80% amplitude by using the auto 80, and I'm going to turn off track mode for this. So I'm just going to set the amplitude of this flaw directly to 80%. Now, whether we use a 3 or 6 dB drop is a function of the pipe diameter, the focusing of the probe, experimentation on notches and side drilled holes, all of these things. But normally in between a 3 and 6 dB drop is where your most accurate readings are going to be. So I'm going to bring the data, the reference and measure cursors here into my area of interest, and I'll zoom back in on this. The color palette that you see at the bottom here is weighted for an 80% orange, a -3 dB right between yellow-orange, and a -6 dB right between green and blue. So it's weighted. So at 3 dB, I'm measuring the length of this flaw at 22 millimeters, and at -6, I would be measuring it at 24. And again, experimentation and procedure and all the operators using the same sizing technique for repeatability is very advantageous to repeatability. So I'll just resume these appropriately. I've got all of my cursors in position, turn on flaw table, add indication, turn cursors off, and we can see the annotation directly here on the S-scan and C-scans, and in the volume-corrected C-scan, we'll see the little box around this. The annotations are only going to be relative to the scan area where the flaw occurs. Okay, I'm going to delete him, and we'll move on to demonstrate a couple other features. I'm going to go back to our regular display here, and we'll take a look at another type of display where we're rolling B-scans. So this is going to demonstrate a couple features that are available in preferences under appearance here for the linking of the beam cursors and the snap to peak. These functions are also available directly from the right click in the header information. So right now I'm going to link the data cursors. So these two data cursors now are linked, so I can roll them both at the same time. When I mentioned dynamic analysis, either using gates or rolling B-scans, the most useful way of finding things that don't belong there in the data is either rolling a B-scan, looking at the entire scan axis of a single beam, and linking the two cursors allows me to do this simultaneously. And I'm just going to add 6 dB soft gain to both of these, so it will exaggerate the B-scan a little bit. I'll zoom back out here. So rolling both of these B-scans at the same time allows me to do the analysis at the same time and saves us a lot of trouble. On any flaw that we see like this one, I would expect it to be detected by both of these. Both of these, whether at different position, so that our link sizing and two probe confirmation can validate the detection. So we will use a little slag and porosity right in the middle of the weld from this sample to demonstrate the snap to peak functions. So if I look at the middle of the weld here, we have a porosity indication here. I'm going to zoom on the UT ruler. I'm going to zoom on the scan axis ruler and reposition it slightly so we can see these two. And again, you saw me do it a couple times. If I double click and maximize the screen, we can see and color and exaggerate directly here. And again, these A32 probes at 5 megahertz are real detection champions for porosity and slag and these typical defects. So the feature now we're going to use is the snap to peak. Okay, I'm going to turn off link cursors. I'm going to turn on my sizing cursors, and I'm going to create a box around the middle of the weld right here. Okay, to find the maximum amplitude pixel within this porosity detection, I can either hunt for it by rolling this using color or by scanning back and forth here, but a faster way is to use the snap to peak. When in snap to peak mode, the software allows me to manipulate my data cursors without doing anything automatically. I can characterize on the S-scan, I can characterize on the data cursor on the scan axis, but as soon as I move any of the reference or measure cursors, the software is going to snap to the hottest pixel in the data, which at this point is at 76% amplitude. And again, it looks a lot hotter than that because I've got some color and a soft gain here as well. So if I look at the other porosity indication here, I've already identified the middle of the weld. So it snaps directly to the maximum amplitude pixel again. So if I zoom out here, and I'm going to move the entire scan axis open. So I'm now performing that function on the entire weld. And we'll just look at some different parts of the weld. Okay, right in here is where we see cracks and notches. So we got a 2-probe detection. I'll zoom back out on here. Okay, if I move over to this side, we see other notches and cracks in that same area here. We're looking for IP right in the middle of the weld right here. So that would normally spike a high amplitude. Let me get all of it in there. Down just a little bit. There's an IP indication in here there it goes. Okay, there's our IP indication. And again, in the volume of the weld is something we take a very close look at for the slag and porosity, which is best detected right here in the middle of the weld. Okay, so we looked at a fracture mechanics type sizing. So now we'll take a look at a amplitude-based sizing. Okay, I'm going to go back to my original display here, and we will take a look at another flaw here. So I've got a 2-probe detection. I can see it here on the SKU90, and it looks like a mess, and we'll explain this. And I can also see it right here on the 270. So this indication is a sidewall lack of fusion that is favorable orientation. I'm bouncing off the first leg right into the second leg here. Okay, you can never know the real size, height, or length of a flaw that's saturated. So one of the first things we'll do is we'll just auto 80 this indication. And I'll bring up my cursors. Oops, so I accidentally left snap to peak off. I'll bring it back here. So here's our guy. So I want to do the depth and the height of this flaw first. So I've already auto-aided it. Okay, I'm going to do a 3 dB drop right on the orange to yellow extremities here and here. So I've got a through wall height dimension of about the size of a weld pass, a little less, 2.2 here. At 6 dB, it would be a little bit larger drop. I'll identify the area on the index axis as well here. So this is a pure amplitude sizing that only works on favorable orientation, typical of sidewall lack of fusion. I'm going to do my linked sizing directly on the C-scan. And you notice the length of this here is going to be a little smaller than the length here of the other side. And we'll talk about that. So what's happening is this has perfect orientation right into the face of the weld. But we have very good supporting information here on the same flaw. So what's happening is we're bouncing off of the ID into the cap right here, which is this area here. Then we're bouncing off of the cap into the far side lack of fusion. And as we bounce off of this cap, it changes angle. It's a rough surface with a cap as welded. So it changes angle, it changes time of flight. We can't trust this position in depth and height or position relative to the weld. But on the scan axis, it's extremely effective for finding the length sizing. So this is where we sized it because it was orientated closer to the probe, but it's still not unrelative that we picked it up here. And use of this type of indication here is also something that customers have justified for their single-sided inspection of pipe to elbows and pipe to components. So we're going to move to the merge functions now, and I'm going to switch data files to a pipe. So I'm going to go File New, just to clear everything out, and I'm going to open up a pipe geometry to demonstrate the merge functions and the polar views. Okay, so we're going to select our layout. I'll double click the data cursor to bring the S scans, and we'll go to piece. And we can see here that this is now a pipe geometry. So when the software is recognizing a pipe, it enables a couple features related to the polar view and the sizing of a pipe. Now again, by loading a piece here, I could convert a plate to a pipe or a pipe to a plate. I can change the geometry, the weld bevel, after I acquire the data in the X3 or in the Focus PX. And there's some more advanced capability to show some types of geometry. That's the subject of our third webinar after this. So I'm going to go to Analysis, Merge, and I'm going to run the merge at a default 0.5 millimeter resolution. So I could have done a shortcut key, or I can come into this form and just select the merge. So this form is hard-coded. Anytime I come into the analysis merge, I'm always going to see the top, side, end, and with a pipe, I'll see the polar view. So by default, all of these views are connected here in projection. That means I have two data cursors. I can see on any one display the projection on the other axes of areas. So our slag and porosity that we were looking at would be right here in the middle of the weld. Okay, we can see it here. We can see it here. Our fusion flaws, I can see on this weld bevel here. Okay, these are on the ID, these are on the OD. So the merge functions are used to visualize the entire volumetric detection of multiple beam sets. And again, with a pipe, we get the polar view here. So one of the first things we do on the merge views is we'll just create a depth window watching the C-scan. I'm going to create a depth window here of about 5 millimeters or so, and I'm just going to walk through the data looking at it at a slice. So we can see flaws start to come in and out. Okay, use of the cursors helps us sort out noise from the root, geometric reflectors, and things like that. So if I take it all the way in the depth slice, I'm watching the C-scan roll through here, and I can see the indications coming in and out. Okay, as soon as I find an indication, I can go check the Toft, or I can, validate it against a single beam set and look at this, or use different displays. So the polar view is very useful. So in this case, I'm going to create a narrow window here on the index axis, watching the polar view. Okay, so when we see flaws like this one, okay, I'm going to move this up here, up. Okay, here's our flaw right here, and we've also seen it here and here. So the benefit of the polar view is we can get real length sizing without having to pull out our calculator and run the calculation to correct the encoder distortion on the outside of the pipe. Okay, so what we're going to do is we're going to go cursors on. We're going to turn off the data cursor for just a second to make it easier to see. Cursors on. Okay, I'm going to place the red reference cursor at the extremity of the flaw and the blue one here to identify the length sizing. And let me bring this back up to get our cursor up here. There we go. Let's bring him over. Bring him back. So the real length of this flaw has to take into account that the encoder is on the outside of the pipe and it's distorting from a square, flat C-scan or B-scan. So I'm going to put the red cursor at the ID of the ID connected flaw and the blue cursor at the extremity here. Oh, let me reverse these two positions. So we can see on the outside of the pipe, without making the correction, we would have measured the length of the flaw at 25 millimeters. And with the polar view or the math correction on the scan axis to account for this at 21.67 millimeters. The polar views or any merge view is available at any time. Cursors off. I'm going to split this display here. Rescale, display layouts. I go down to my merge views here, and we can put the polar end views here or in the display and save that in our layout the same way that we would have from the fixed merge views there. And if that is after you run the merge, the 3D image is available as well. So right now, the 3D image is using a series of defaults that we designed in our to-do list for future version. We'll have the form that allows more customization of this and some readouts associated with it. It's more of a brochure feature than in a real practical value. Okay, so we're going to look at one more indication, one more flaw typical of something we do a lot of, which is the LNG work. So I'm going to switch to an LNG acquisition that's using a quad probe like this one. Okay, this is DLA and shear wave probes all wired into a single connector, which is an Olympus solution for LNG. The 4 megahertz A27 probes are ideal for the I-625 dissimilar metal welds of CRA piping and LNG tanks. This is a 9% nickel base material with an I-625 weld here. And the beam tool that represents that for the quad probe, we visualize here. So we're taking 4 S scans from 6 probe housings. So the DLAs are pitch catching. The DLAs inspect the center of the weld. The shear wave probes inspect the outside bevel. So what we'll do in this data, we use the same display layouts for acquisition and analysis. So I'll look at the benefit of the shear wave inspection, like we see right here, is for all of the bevel flaws. We have to prove a lot of accuracy during the qualification tests, and many of the flaws are bevel flaws. The 4 megahertz probe is uniquely suited for the Inconel inspection. We can see the weld bevel right here. And again, our ability to accurately size bevel flaws on the B scan and the S scan means that we don't have to do that on the DLAs that would degrade the accuracy a little bit. So the main flaw that we see in LNG tanks that accounts for most of our repairs, and the one that's impossible to detect and size without the use of a refracted longitudinal beam, is the round trip tandem indication. So if we look on this S-scan, okay, this is the volumetric location of the flaw that can be as low amplitude that you can't even detect it. This is the round trip tandem signal that's a result of the LLT or the TLL that always shows up. So our link sizing and detection, we use this indication. What that looks like, whether you understand it or not, this is this mode of propagation. When the flaw is right behind the direct L, like it is here, right behind the direct L, we know it's the TLL or the LLT. And it doesn't really matter for what I'm about to explain if you understand the beam dynamics, as long as you know where to look and what to look for. So how we would size this flaw, we would zoom on the axes, we'll go to a single beam set, and I'll bring up the DLA here, zoom appropriately. Okay, we linked size this flaw using the round trip tandem indication, meaning this signal here can be trusted to a greater extent than the direct L. So we performed the link sizing on the indication that shows up best on the scan axes. But the actual depth and height of this flaw is managed on the S-scan. So without a clear tip in austenitic material, this is very typical. We would estimate an amplitude drop here. So one method would be just to increase the color until the very first part of the orange shows up like it does here. The flaws are typically smaller than you think they are, and we would normally oversize them, so be very conservative. And about the size of a weld pass is what almost all of these flaws end up being on the qualification tests, and a little smaller in the field. So this is an L-wave technique using a DLA compression probe. And again, a very good bundled solution for use of shear wave pulse echo and DLA probes for LNG tanks, for CRA piping, etc. So I'm going to end it there. Our next webinar is going to include some advanced geometry updates, use of the recording of the flaw table and reporting for the custom Excel report. And we look forward to all of you joining us then. So thank you very much for attending. I saw some questions in the question and answer that we'll respond to in the email blast that we send. If you are interested in a WeldSight, a Focus PX, or an X3, please contact your local Olympus Service Center. And with that, I'll turn it back over to our moderator, and thanks again for joining us.
Chris, on behalf of Olympus, I'd like to today for joining us. We hope this material presented was informative and useful. This webinar will be archived on our website at www.olympus-ims.com. As I said before, everyone who registered for the event will receive a follow-up email with links to the archived presentation. That's going to do it for today. I'm going to leave the webinar open just for a little bit longer. If anybody has other questions they want to type in, and we'll gather them up and get them over to Chris after the event is done. So that's going to do it for today. Thanks for your interest and taking the time to attend the event, and we'll see you again next time.